Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical, and we are talking about the welding of metals. In this particular presentation I will be talking about the heat affected zone in the transformation hardening metals, particularly ferrous metals, like it may be cast iron, it may be steel, high carbon steel, low carbon steel, or the medium carbon steel. So, the heat affected zone formation study is important because this is the zone which is affected by the heat supplied during the welding, and this zone experiences the changes in terms of the microstructure and mechanical properties. So, when these changes occur, many times we find the properties which are not acceptable for the given application. Therefore, it becomes important to bring the properties which are within the acceptable limit through the post weld treatments, which may be in form of in various forms. Okay. So, initially we will be talking about the weld thermal cycle, which is induced in the zone next to the fusion boundary due to the heat applied for melting the fin surfaces in fusion welding. Okay. And thereafter we will try to relate the weld thermal cycle with the heat affected zone formation in the transformation hardening metal like steel. Okay. So, we know that during the welding, when the heat is supplied, say in this particular case the two plates being welded, okay, and there is a heat source. So, this is the heat source which may be in form of like say the flame or arc or laser, anything. So, this is the welded section. When the heat is applied during the welding using suitable source, no? So, not just the melting of fin surfaces will be happening, but also a zone is formed which is adjacent to the weld metal zone, where the heat will be dissipated and the changes will be experienced in form of the microstructure and the properties of the base material. So, that zone which will be experiencing the changes due to the heat applied will be termed as the heat affected zone. Okay. So, this formation of the heat affected zone heavily depends on the location and the kind of thermal cycle which is experienced by the metal. Okay. So, if we see to see like what kind of thermal cycle experienced by the metal, that will depend upon the location where it is location or the point of interest. Say if we see the point A, which is little closer to the relatively closer to the fusion zone as compared to the point B. Okay. So, when the heat source approaches these points, so there is an initial rise in temperature. The rise in temperature is much faster and to the greater level. So, the peak the location experiences higher heating rate, okay, and higher peak temperature. Okay. If we talk about these two aspects, then the location B, okay, location B, which is little away from the weld center line, that will be experiencing lower heating rate, lower peak temperature, and likewise higher cooling rate will be experienced by the location A, and the lower cooling rate will be experienced by the location, the metal in the location B. Another important aspect is like how long a particular temperature is maintained. Like say if the critical temperature is this, okay, say this is the critical temperature above which the change in properties are experienced in the metal. So, how long that temperature is maintained, that will affect the severity of the heat on the changes in structure and properties. So, if we see the location B experiences the high temperature retention above critical temperature is for a shorter period as compared to the location A, where the change is experienced for much longer time. Okay. So, these are the first thing is these are three important aspects about which we can get the information, like the first is the heating rate, then the peak temperature, then the soaking time above particular temperature of interest, and then the cooling rate. Okay. And there are three important aspects which significantly affect the formation of the heat affected zone, means the kind of changes which will be experienced by the metal in terms of the microstructure and properties, that will heavily depend on the peak temperature that is experienced one, soaking time is another, and the cooling rate is third. Okay. So, we need to see these three aspects, and this in case of the ferrous metals like say in iron carbon systems, which are primarily like in form of cast iron or in form of steels like. So, in depending upon the composition of the steel, this critical temperature will be affected, critical temperature will be different, and the how fast and how slow the response in terms of the microstructural changes and mechanical property is experienced, that will depend on the composition of the ferrous system which is there. So, when we apply heat and a particular point or location close to the fusion boundary, when it experiences weld thermal cycle, it experiences also the change in phases and the change in grain structure. So, the zones which are next to the fusion boundary, that experiences higher temperature for longer time. So, it shows coarser grains as compared to the zones which are away from the fusion boundary, they will be experiencing higher temperature for relatively shorter time, and that shows the fine grain. Okay. And accordingly, we have the terms like coarse grained heat affected zone and fine grained heat affected zone. So, where what kind of the grain size that will be formed, about that we will be talking little later, and what kind of phase transformation will be happening, about that we will also be talking little later. So, we know that when the cooling rate is slow, it promotes the formation of like coarse pearlite. Further higher cooling rate will be leading to the, so this is for slow cooling. When little medium cooling rate, then we will be getting the fine pearlite. Okay. Further higher cooling rate will be resulting the combination of pearlite and martensite, and very high cooling rate will be resulting in the martensite, and information about these we can get simply from the CCT diagram. Okay. So, what is the minimum temperature above which a steel or ferrous system should be heated, so that it will be experiencing the change in properties, that will primarily depend upon the one is the critical temperature, like say lower critical temperature in case of the carbon steels or alloy steels, or it can also be the recrystallization temperature. Okay, depending upon the condition of the metal, whether it is in work hardened condition or anneal condition or a particular heat treatment condition. So, the point here is when the ferrous system is subjected to the welding, it experiences lot of changes in the zone next to the fusion boundary, and those changes are experienced in form of the phase transformation. Okay. So, your simple ferrite and pearlite may convert into the like pearlite or martensite or completely martensite or mixture of the pearlite and bainite, depending upon the composition of the steel or the ferrous system which is in consideration. So, it can experience a lot of changes, but an unaffected the base metal may simply have ferrite and pearlite only. Okay. So, the changes or the kind of phase formation that will be experienced in the heat affected zone, that will depend upon the weld thermal cycle WTC and the composition of the metal itself. Okay. Because the composition effect determines the carbon equivalent, which in turn determines the hardenability, and hardenability determines the kind of the cooling rate that will be encountered during the welding at a particular location, that will be producing which kind of the phase. So, about these aspects we will be talking in a little greater detail in the coming slides. So, we know that the ferrous system, and that we can understand best with the help of the iron carbon diagram. Okay. So, in iron carbon diagram we know like this is the say one typical iron carbon diagram for so say for a particular carbon content, say it is 0.3% carbon steel. Okay. So, what happens when it is heated during the welding? We know that say this is the 0.3% carbon steel. Okay. And this is the fusion boundary. So, obviously it would have experienced the temperature greater than the melting point. Okay. So, let us talk about little bit like what happens when the base metal at 24 degree centigrade, when it is heated to the higher temperature, say up to 200 degree centigrade, there is no major change, but the temperature greater than 200 or say greater than 400 degree centigrade, that will be experiencing the recrystallization Okay, this is one. Then the second critical temperature, this is one temperature at which the changes will be experienced in form of formation of new grains, that will be termed as recrystallization. Second temperature limit is the lower critical temperature, LCT. Okay, this is the lower critical temperature, this is the recrystallization temperature. So, all the zones which are being heated above the lower critical temperature, so they will be experiencing the austenite formation, initial mixture of ferrite and austenite. Okay, and if it is the hyper eutectoid steel, then there will be cementite and austenite. Okay, those temperatures. So if we go further, little higher temperature above the upper critical temperature. So this is the another limit, UCT. Okay, so yeah, so this is a lower critical temperature 727 degrees centigrade. If you go further higher, say about 900 degrees centigrade, then that is upper critical temperature for this say particular composition. Okay. So, here above this temperature we will have just austenite, that is all. So, here this austenite, okay, this austenite, if it is, so this austenite, obviously the temperature, high temperature being retained for a shorter time. So, if we see the formation of particular kind of phase, that will depend upon the temperature, that is what we can easily see from the iron carbon diagram, but this corresponds to the equilibrium condition, means there is enough time being given for exposure at a particular temperature to form particular kind of phase. But in reality, during the welding, the high temperature is or temperature at which a particular zone is maintained, that is for very short, that is for very short time. Okay. So, if we see here, we have ferrite and pearlite. Okay. So, this will be maintained, ferrite and pearlite will be maintained until we go above the lower critical temperature, although new grains may form above the recrystallization temperature. Okay. Ferrite and pearlite will be maintained, and thereafter our the pearlite will transform into the austenite and ferrite will remain as it is. But here part of the ferrite will be converting into the austenite depending upon the temperature range. So, this will be termed as the temperature between the lower critical temperature and upper critical temperature is known as intercritical temperature. Okay, intercritical temperature. So, when the metal is heated, all the zones which are heated during the welding in the intercritical zone, intercritical temperature range, that zone will be having a mix of austenite plus ferrite, and the zones which are heated above the upper critical temperature, they will be having the austenite only. Okay, that is all. So, now we will try to see the things little in better detail. Okay. So, what happens when the cooling is done to from these different conditions. Okay. So, let me just erase it out. So, say okay. So, before cooling, let us talk about the soaking aspect, like say these phases will be formed in very homogeneous condition only if high temperature is maintained for longer time, so that the equilibrium state is attained, but during the welding that is not the case. So, let us say for example, the temperature versus soaking time relationship, if we see in case of the steels to form the homogeneous austenite, that is very long. So, initially if we see, if there is an alloy steel having the, like say certainly carbon, iron and some carbides like vanadium, titanium, carbide forming elements, chromium, etc. Okay. So, what happens at the room temperature, steel may be having ferrite, pearlite and alloy carbides. So, initially when things are heated, initially the pearlite will transform into the austenite. Okay. And then ferrite and alloy carbides will remain as it is. Thereafter, the ferrite will convert into the austenite and then we will have the alloy carbides. Thereafter, alloy carbides will decompose. So, the alloy carbides will be the last constituents to decompose and contribute towards the formation of the homogeneous austenite. So, it means that the different phases decompose into the austenite gradually. Okay, they convert into the transform into the austenite gradually. They will take, and there are different stages. So, it will take longer time to convert the homogeneous all these constituents like ferrite, pearlite and alloy carbides into the austenite. It will take long time, but the time dependent is also function of the temperature, shorter time at a higher temperature and longer time at lower temperature. Okay. So, but during the welding we may not have this kind of luxury where homogeneity is attained, because the weld thermal cycle is maintained for high temperature, is maintained for shorter time. Okay. So, what will be the effect of this high temperature retention for shorter time is this, that whatever will be formed, that whatever the phase transformation is taking place from the ferrite, pearlite and alloy carbides into the austenite, okay, that will be either partial, this is one, or it will be heterogeneous, not the homogeneous. Okay. Heterogeneous kind of heterogeneous austenite will be formed. Okay. So, the partial transformation is partial and it is heterogeneous, means it is not uniform in terms of the composition across the grains. So, as a result of this we get lot of heterogeneity in terms of the microstructure and the phase transformations that will be realized during the cooling. Okay. So, this is the another aspect, like one is that high temperature is changing, you see this is the fusion boundary, okay, and as a function of the location 1, 2, 3, 4, if we try to measure if we try to plot the temperature, then what we will find, temperature at 1 is high, then at 2 is little low, for 3 at further low, and 4 is further low. So, peak temperature is decreasing, this is one. Soaking time is also decreasing at a higher temperature. So, this is about the peak temperature as a function of time. Likewise, soaking time as a function of the location will also be decreasing. Okay. So, with the increasing distance we will be having the lower peak temperature and shorter soaking time, and that will encourage the kind of, these two conditions will encourage significant heterogeneity. Say here and very next to the fusion boundary we have got the austenite, next to that we will have ferrite plus alpha ferrite plus austenite, next to that we will have the ferrite plus pearlite. Say these are three zones, okay, which are being formed. So, what will happen during the cooling, because the cooling conditions which are experienced during the welding are very high. So, the high cooling rate experienced by the metal next to the fusion boundary, especially this usually converts the austenite into the martensite. Okay. But here ferrite will remain as it is, but this austenite can convert into the martensite or it can convert into the fine pearlite, okay, depending upon the carbon content in steel. Okay. And even if the martensite is being found, it will be of the low carbon martensite, and other zones will be left as it is like ferrite and pearlite. So, what we are going to have, like the coarse austenite will transform into the coarse martensite. Okay. So, initially we get the coarse martensite next to the fusion boundary, then we get the fine, very fine pearlite or ferrite, okay, or martensite. So, fine pearlitic, martensitic or the ferritic structure is attained. So, and then we will have the unaffected zone ferrite and pearlite. So, this is the base metal, this is the fine grained Z, okay, and this is the coarse grained HAZ. Okay. So, this is these things are based on the principles related with the triple T diagram and CCT diagrams. Okay. About that we will be talking in the next slide. So, what we have seen is during the welding, the zones next to the fusion boundary, they are heated to the different temperatures. Higher the peak temperature attained at the location which is close to the fusion boundary. Okay. So, say what happens when a particular temperature is maintained until the transformation of austenite completes into the other phases. So, that is what we can see from the isothermal transformation diagram, like if the high temperature austenite is there and if the high temperature is maintained at say around 680 degrees centigrade, then initially the austenite transforms into the austenite will transform into the pearlite. This is the two phase zone and then it will be completely converting into the pearlite. Okay. So, initially we will get the coarse pearlite. Then if we hold the steel at a higher temperature, say 600 degrees centigrade, then we will be getting the fine pearlite. So, lower, if we keep on reducing the high temperature retention period, high temperature retention at a constant temperature, say 500 degrees centigrade at the nose, it will be producing the very fine pearlite. Then we will be getting the coarse bainite, then fine bainite. These are the principles related with the isothermal transformation. If the steel from the homogeneous austenitic state is directly quenched in the temperature below the MS temperature, then it will be converting into the martensite immediately. Depending upon the temperature at which it is being quenched, the austenite will be transforming into the martensite. If it is below the MF temperature, then 100% austenite will convert into the martensite. Okay. But during the welding, it does not happen in that way. This triple T diagram simply helps in to understand what are the different phases that will be formed when the isothermal temperature is maintained from the austenitic state. Okay. But during the welding, the cooling is continuous, it is not fixed. So, if we see the zones which are next to the fusion boundary, they will be cooled at very fast, cooling rapidly, but the zones which are away, they will be cooling slowly, further slowly. So, the cooling rate experienced by the steel during the welding, that will be changing with the location, that is one. Okay. And so, if the steel is hardenable, so depending upon the cooling rate that it is experiencing, it will be forming different phases. Say, so zone next to the fusion boundary, if it is forming complete austenite, due to the rapid cooling, it will be forming martensite. So, that is what we can see from this CCT diagram. So, here you see, say we are talking about the zones which have been heated to the austenitic state or partial austenitic state. So, say the zone next to the fusion boundary here has been heated to the higher temperature. So, this will be completely in austenitic state, and this zone will also be experiencing the higher cooling rate. Okay. So, it will be converting whole of the austenite into the martensite. So, here at the cooling rate, another location next to the fusion near the fusion boundary, if that is also experiencing the higher cooling rate greater than the critical cooling rate, then this will also be converting into the martensite. So, this zone will be having the complete martensitic formation. If the zones which are further away from the fusion boundary, they will be experiencing little lower cooling rate, and there what will have, maybe part of the austenite, a part of austenite will be transforming into the martensite, plus it will also be forming the pearlite. Further away, if it is the Cr2, then here we will be having the fine pearlite formation. Okay. And the further away locations. So, the point here is the locations will be experiencing the different cooling rates, and accordingly the different phases will be formed, and that is why. So, there are three aspects: neither our peak temperature adjacent to the fusion boundary is uniform, okay, nor our soaking time is uniform, nor our cooling rate is uniform, and that is why the kind of phases that are experienced in the heat kind of phases that are found, kind of microstructure which is observed, kind of mechanical properties which are obtained in the heat affected zone, they show lot of heterogeneity and non-uniformity. Okay. So, this is about the kind of the changes that will be experienced by the ferrous metals due to the weld thermal cycle being imposed. This is what we can understand, okay, from this iron carbon diagram as well as the weld thermal cycle and the temperature being attained. So, if we see, say for particular carbon content in steel, so this is the two phase zone. Okay. So, all the metal next to the fusion boundary which is heated in this mushy zone temperature range, that will be in the partial melting state. So, it will be partial melting zone where we will have both solid as well as liquid. Solid is our delta ferrite and liquid metal. Okay. But below this we have the another zone. Okay. This is the zone where we will have the austenitic state, complete austenitic state, and this will be forming the coarse heat affected zone, and then we will have the intercritical temperature zone. Okay. The zone which is heated in the intercritical temperature range. So, this will be the fine grained heat affected zone, and then there will be a zone which will be heated above the recrystallization temperature, but below the lower critical temperature. So, that zone will be under the recrystallized zone, and then unaffected base metal. So, this is how we can understand the different zones next to the fusion boundary are heated to the different temperatures, and accordingly they form the different microstructural features and the different, and accordingly it offers the mechanical properties. So, coarse grained heat affected zone usually offers the coarse martensite. Okay. Fine grained heat affected zone, as per the cooling rate encountered, it may offer the fine grained pearlite, fine grained ferrite or fine martensite. Okay. Then we have the recrystallized grains. Okay. So, it is possible like the heat affected zone may experience significant hardening. Okay. And also if the base metal if the weld metal is being developed through the autogeneous welding, then certainly it will be showing the maximum hardness like this, like this. So, here this is corresponding to the weld, this corresponds to the HZ, and this is corresponding to the, say, the sharp transitions taking place in the fine grained zone to the base metal. Okay. So, going to the next, now the solid state versus the fusion joining process as far as the steel is concerned. So, if we talk of the fusion welding, in fusion welding the approach is like melting the fin surfaces and followed by the solidification will produce the weld joint. But during the welding, thermal cycle imposed is very severe, so it results in significant the phase transformation. Okay. Heat input delivered during the fusion welding is much higher, and therefore it results in the wider heat affected zone. And since there is a molten metal and which during the solidification, through the solidification will be producing the metallic continuity for producing the weld joint, we come across, so because of this melting followed by solidification, we come across the issues like solidification cracking, liquefaction cracking, porosity and inclusions. Okay. On the other hand, if we talk of the solid state joining process, there is no melting and solidification. So, we do not come across the issues related to the melting and solidification. Since the heat input during the solid state joining process is somewhat lesser, so the weld thermal cycle and the related issues are somewhat less. But during the solid state joining processes, we can have the work hardening effect apart from the phase transformation due to the heat being generated during the solid state joining process. Relatively less heat used during the solid state joining process results in the relatively narrow heat affected zone, and because of the absence of the melting and solidification, there is no solidification cracking, liquefaction cracking, porosity or inclusion related issues. So, now I will summarize this presentation. In this presentation, basically I have talked about the weld thermal cycle and how weld thermal cycle produces the different types of the zone in the heat affected zone, different types of the zone in the zone next to the fusion boundary during the welding of the steels. Thank you for your attention.